Welcome to Lesson 5. Lesson 5 deals with simultaneity in panel data, and I am Teodosio Pérez Amaral, and I'm going to help you with this topic, which is a very important topic and very useful, and it seems complicated at the beginning, but at the end it's relatively easy to deal with, and Stata helps us a lot to deal with this problem. Let me start with some general remarks about simultaneity. The idea is that I'm going to follow first an exposition of the simultaneity problem without panel data, and then we are going to introduce panel data. So at the beginning of this lesson, we are only going to deal with cases in which we have like time series or cross section, but we don't have panel data. The reason is that it is more intuitive to start with this type of framework and then go to the panel data framework. And let me start with telling you that simultaneity is a common situation in economics and in other disciplines. It is common because it is very typical to have a situation in which there are two or more variables that are endogenous, that are generated within a system of equations, and in that case the two variables are jointly determined, and we cannot really separate the generation of one variable from the generation of the other variable. Let me start with a very simple example, which is a model of supply and demand, and we have therefore two equations and a balance condition. The equations are a supply equation Q super S sub t, and then that is equal to alpha 1 plus alpha 2 pt plus u1 t. This would be a supply equation, and this is telling us that the quantity of a good or service that is supplied depends on price, and the price has a positive effect, which is measured by alpha 2. And that would be a straight line, and it has an intercept that is now alpha 1. On the other hand, we have another equation that is the demand equation, and the demand equation is beta 1 plus beta 2 pt plus beta 3 yt plus u sub 2 t. This is a demand equation. This is telling us how the demand works, how much quantity are the consumers ready to buy depending on the price and the income, which is y. Typically beta 2 is going to be negative, so the higher the price, the lower the quantity, and typically also the beta 3, which is the effect of the income, is going to be positive. We don't know for sure what is the size or the sign of alpha 1 and beta 2. We also have error terms, u1 and u2, and those arise from the possibility of having relationships that are not exact, that are only approximations, and there may be other factors that also intervene in the supply and the demand, and that are moving the supply and the demand in specific ways. Then we have a balance condition, which is that the quantity of each of the two equations should be equal to each other, and then we will have also that we have endogenous variables, which are Q and P. They are endogenously determined in this system of equations, and this is a typical situation in economics. We have also an exogenous variable, Y, which is the income, and it's determined outside this system. This is a very basic system, something that we observed in economics in the very first days of a class of the first course. So this is very simple and very typical, yet it presents some problems. The structural form that we just saw is a system of simultaneous equations, and they are equations that reflect economic behavior, and the parameters have an economic interpretation. Economic theory suggests which variables are exogenous, which variables are endogenous, and which variables belong and do not belong in each of the equations. That is our basic setup. The problem with the previous structural equation is that if we try to estimate it using the typical estimates that we use, OLS or other estimators, typically we find that the estimates of the relevant parameters are inconsistent. Inconsistent means basically that they are hopeless. We cannot do anything with them because they are not going to approximate any value of interest. The reduced form, on the other hand, is like a trick that we are going to perform, and the trick is going to help us in estimate in a way that may be a little better than the previous one. The reduced form is writing the system of equations so that each endogenous variable is a function only of the exogenous and predetermined variables. So essentially what we try to do is we just try to write the system in a different way, in which we have one equation for each endogenous variable. That is just solving a system of equations. That is something that you know how to do since you were like 13 or 14 years old. This is not anything that is mysterious or strange. That is something that is very simple, that you know how to do, and that you forgot already how to do it. What happens when you solve a system of equations like this, even a simple one like this? It happens that the parameters of the reduced form are combinations of those of the structural form, and those parameters that are combination of a structural form cannot always be disentangled, cannot be recovered from the reduced form parameters. And this is what we call the identification problem. Identification may mean different things in different contexts, but in our context it means how we solve and find the value of the alphas and betas of the structural form from the values of the parameters that we can estimate from the reduced form. Let's see now an example of what we have just seen. An example is this. This is a qt equals pi 1 1 plus pi 2 1 y t plus v 1 t. This is another equation. This is an equation that we can obtain by solving the previous two simultaneous equations, and this is an equation just for q. It is just a function of the exogenous variables and predetermined variables, in this case only income y, and we also have a second equation pi 1 2 plus pi to 2yt plus v 2t. This is a second equation which is telling us how pt, the price, behaves. We have then two equations, one for quantity, one for price. And the good thing about these reduced form equations is that we can estimate pi 1 1, pi 2 1, pi 1 2, and pi 2 2 using ordinary least squares. That is the good news. The bad news is that sometimes we cannot recover alpha and betas because the relationship between alphas and betas is not that straightforward. You see here in the lower part of the transparency that we have a relationship between the pi's and the alphas which is not that easy, not that direct. Sometimes we can recover all, sometimes we can recover some, sometimes we cannot recover any of the alphas and betas from this set of equations here, and that is precisely what is the identification problem. Identification means try to recover alphas and betas from pi's. So this would be to solve a system of equations, in this case this system of equations, and this system of equations you can solve it sometimes when some conditions are met, and cannot solve it other times when some conditions are not met. It just happens that these conditions are known to you since you were 13 or 14, and of course they are forgotten now, mostly forgotten, but let's see if we can just recall a little bit about them, and I'm sure that they will ring bells. Let's continue also talking about the concept of identification and how we could possibly get some identification from basic, simple conditions. Let's go now to a graphical example and see what identification means in terms of graphs. The idea of identification is the recovery of the parameters of the structural form from the reduced form parameters. It is important because we can estimate the reduced form parameters well by OLS, but the OLS estimates of the structural equations form are inconsistent. So it is important, the identification problem. Let us see now below what happens when we have structural equations and we are still struggling with identification. See that in this particular case we have price and quantity. In the vertical axis we have price, in the horizontal axis we have quantity. This is a typical way in which economists draw the pictures. And if you look at this, you see that we have two S's and two D's. The two S's are supplies, and those supplies, which are upward sloping, are telling you that we have a situation in which the higher the price of the market, the higher the quantity is supplied by the firms or the suppliers. We have two supplies because capital S1 and capital S2, we have two of them because they are different. They happen in different moments in time, and that's why there are two of them. Then we also have two demands that are in downward sloping, and there are two of them because they happen in different moments in time. We also have like 2 points, which I put a circle around them, A and B, and those 2 points are related to equilibrium quantities and price for supply and demand 1 and for supply and demand 2. Those are A and B, and the equilibrium prices and quantities are what we observe. We observe just those 2 points, A and B. Those 2 points, A and B, are interesting. They are equilibrium points, but the question is, how much do we learn about the position and the size of the supply and demand by knowing what equilibrium points A and B we have? Well, if you think about it, the solution is that we know very little. We know very little because in A or in B, we don't know what is the shape of the demand or supply, and we don't even know whether they have shifted or not. We just don't know very much about that. But that is the typical situation in which we observe A and B, but A and B are not very informative at all. This slide, number 7, is very important, and it's very important that you pay attention to it and understand what this says. In the upper panel, you see the situation in which there are several supplies that you can think of happening at different moments in time, or also happening under different values of income, or different values of wages, or different values of conditions that may influence the supply. You also see that there is one demand that is downward sloping. It's D sub 1, and then you see also some points A, B, and C of equilibrium that would be observed in the real world. Here it would be very nice if we had some variable or some condition that would move the supply along time or along different values of different variables, and it would draw the shape of D1. So moving the supplies S0, S1, S2, and probably more S's would help us draw the shape of D1. That would be great. It would be wonderful if we had some variable that moves the supply and doesn't move the demand. So that variable would help us make the trick of identification. It would help us identify the demand if there is some variable that moves the supply and does not move the demand. In the same way, in the lower panel, you have situations in which you have a supply S0 and you have several demands S D0, D1, D2, D3, and those are moving. The demands are moving. Why are they moving? Well, think of the possibility of that there is a variable that moves around but only affects demand and does not affect supply. That would be very convenient, very nice, and that is typically the case in which we can identify a supply by having a variable that moves demands around but does not affect supply. So the trick here is having variables that affect one of the curves but do not affect the other. So that would be a great situation, a situation that actually is the basis for identification, and you can see graphically what that means. That is the right intuition that I'm giving you, and that it makes a lot of sense thinking about this in this way. In terms of equations, and we go back to equations now, to solve the problem of identification, that is to recover the parameters of the structural form from the reduced form, we have to solve a system of equations. The system of equations I am referring to now is not the structural equations, it is the equations that relate the alphas and the betas. So this is the question here: how to recover alphas and betas from the system of equations, from the second system of equations that we saw. Now, how can we, what are the conditions that we need to solve a system of equations? Well, this is something that you know from your early childhood, and you may remember or not, but the idea is that if you have the same number of equations as unknowns, a particular equation is identified. So if you have the same number of equations in the pi alpha beta system, then the structural equation is identified. Then if you have more unknowns than equations, then your structural equation is unidentified and or sub-identified. And then if there are more equations than unknowns, the equation is over-identified. You have several estimates for the same parameter. So this is the basics of identification. The idea, the specific idea of identification when we go to the panel data framework is similar to this, and it is very simple, and you will see that the rule is extremely simple. You don't have to really solve equations. Now, if you think about estimating a system of simultaneous equations, what you have to have in your mind is, if you try OLS on the structural model, you're going to get biased and inconsistent estimates. So this is hopeless. If you go to the reduced form and estimate by OLS, it may happen that you have certain equations that are exactly identified, and we can recover the structural form parameters, and in some other cases you cannot recover them. So that is the situation with the reduced form. Recovering the parameters of the of the structural equation from the reduced form involves a special estimation technique, which is indirect least squares. It is very simple because the only thing you have to do is you have to estimate the parameters of the reduced form by OLS, and then next what you have to do is try to recover the alphas and betas from the pi's that you get estimating the reduced form parameters equations. In general, the estimation is biased and consistent, and well, it is possible to do it. It is possible to do it sometimes, only sometimes. However, what we want to show here and introduce now is an estimator which is simple and which is very powerful, something that we talked about already in lesson 4, and it is instrumental variables. The instrumental variables are useful for estimating exactly identified equations, and this is an estimator which is more general than the OLS estimator. It has very nice properties because it is consistent and asymptotically normal. And in this particular case, it has very nice properties also, because you can find candidate instrumental variables easily, because you can have variables that do not appear as explanatory variables in an equation, and then those are the candidates instrumental variables. So the idea is you need instrumental variables for one equation. What are the candidates? The candidates are variables that do not appear in that equation but appear in a different equation of the system. There are a couple of drawbacks to these instrumental variables techniques, and it is that they are not unique and they are not efficient. This is something that I told you already in the previous lesson, and this is a problem that we have here also. In the previous lesson we were thinking of solving it using two-stage least squares or Arellano and Bond, and then here we will try to solve it also in some other ways. Again, this number 12 tells you that we need instrumental variables, and we need instrumental variables as an alternative to OLS, because it performs better in large samples, and the two conditions that we need, the same as in lesson 4, the two conditions that we need to have instrumental variables that are useful for our purposes is, first condition, the instrumental variables are not related to the error. Then second condition, that the instrumental variables are related, have correlation with the explanatory variables. Those two conditions are important. You have to keep them in mind, and we'll use them later. If those conditions are in place, then we can write the formula of an estimator, which is the instrumental variable estimator, and that is equal to z prime x to the minus 1 z prime y. So let me remind you what this is. This is a formula, a closed formula that helps us guess good approximations for the betas that are unknown, and those techniques are going to help us if we plug the observed y's in this formula, we plug the observed z's in this formula, and we plug the observed x's in this formula. So this is basically similar to x prime x to the minus 1 x prime y, the OLS estimator, but more general, because this is a case in which you may have instrumental variables, and the instrumental variables are going to help us get consistency, which OLS does not guarantee. Sometimes you have x's and z's that have variables in common. This is no problem. You only need to instrument the variables that present problems of correlation with the error, and those variables that are x's and do not have problems, those are going to function as instrumental variables for themselves. So summing up this transparency 13, no problem if you have x's that are not instrumental variables but are uncorrelated with the error. Those are going to work as usual, no problem. Again, we find here in this transparency the formula of instrumental variables. This is something that I want you to get used to. You see that the z's are the matrix of observations of the instrumental variables. Some of them may coincide with the x's, so, but they need not to, they may. And the c prime x should be invertible in order to be able to compute the incremental variable estimator. But that's something that is common in these situations. Why is the incremental variable useful? It is useful because it is consistent and asymptotically normal. Here are some conditions and some proofs of the consistency of the incremental variable estimator. I'm not going to go through this because this is essentially because this belongs to a previous course. In a previous course, you should have seen why incremental variables are useful and what is the behavior of incremental variables. So that's the reason I'm not going to go in detail through this formulation. Again, here in 16, you find that you have the assumptions of the general, in this case, the general linear model. You have the typical assumptions. Now the assumption 6 is substituted by x's being stochastic, but that is the same as you have seen from introductory econometrics. Nothing new except assumption S6. Again, the incremental variable estimator. This is the proof of consistency. I'm not going to go through this in detail because you should know, and if you don't know, it doesn't matter because you just believe it, and that's enough. The asymptotic normality of the incremental variable estimator is a very important property. It is very useful because it allows you to do inference, and that means that you can use the t-test and f-test and chi-square test as usual. It is a very important property, very useful, and this is something that we are going to be using all the time, even without noticing. The asymptotic normality means that the incremental variable estimator is not exactly normal, but it is approximately normal. Approximately normal for sample sizes that are large enough. Large enough depends on the situation, but typically for the sizes of sample that we are going to use in panel data, that will happen most of the time. I'm not going to go in detail through this, but this is just telling you what is the asymptotic normality in terms of equations. This is transparency number 19. Efficiency of the incremental variable estimator, transparency 20, is very important, and the idea is that in general incremental variables estimators are not efficient. It is always possible to increase their efficiency by increasing the number of incremental variables, and the idea here is just include more and more instrumental variables to make more efficient the estimation of the relevant parameters. What we do typically is, in this case, use several or many instrumental variables to approximate the the values of the parameters we care about, and we use two-stage least squares. Two-stage least squares is very useful in this case because what it does is includes more and more instruments. You see here, including x2, including x3, more and more instruments to be able to get good estimates. What we do here is just similar to the case of the Arellano and Bond estimator, including more and more instrumental variables. In the Ariane bond it was lag values, and here is just more and more variables that do not belong in the equation but are in other equations of the system. The two-stage least squares that we care about in this case are better behaved than in the previous ones because they are consistent, asymptotically normal, and they are efficient, so that they are optimal in a sense, because they incorporate more information than just using one instrumental variable. Now, with those ideas in mind, let me jump into the situation of simultaneous equations model. In the simultaneous equation model, we have exactly the same problems and very similar solutions when we are talking about a system of simultaneous equations that we may write in similar ways as in the previous cases. Let me tell you now what is the structural form with panel data. The structural form would have now a matrix of capital gamma coefficients, and those capital gamma coefficients would have a size of capital G times capital G. The idea of these coefficients is that they belong to variables that are endogenous. So those are the coefficients that have, say, in the right hand side, have endogenous variables that are affecting the variable that is the variable of interest in one equation. So that is the reason why we have a matrix of coefficients here, and the matrix of coefficients is just a matrix of the coefficients of each endogenous variable on the other endogenous variables. Typically, the coefficients are going to be have some interpretation, economic interpretation, and so that is how you find out which ones are coefficients are inside capital gamma. Then you also find a set of coefficients which is a capital G times K, and those are the beta coefficients, and those are the coefficients that are measuring the effect of variables that are explanatory variables, typically exogenous variables, on the endogenous variable. So that would be the system here. That would be capital gamma times YIT plus beta XIT plus nu, and that is equal to nu IT. In general, the notation is the same as before, but now we have an extra dimension, and that goes in the direction of the number of equations that we have now, because in the previous cases lessons we had only one equation, but now we may have several. Several means 2, 10, 20, whatever number is appropriate in each case. In principle, we are going to deal with an error component model. It need not be the case, but we are going to allow for an error component model which has components that are typical, the ones that you have seen already. Then it comes the case in which it appears a lot of restrictions, a lot of situations. Here they are just telling us one thing: everything is fine, everything is has no problem, everything works fantastically well. And the problem that we are going to find, simultaneity, is going to be isolated. We want to isolate this model and stay just with the core of the problem, which is simultaneity. We don't want to mess the situation with all other possible problems, and that is why we make all those assumptions telling us, look, there are no other problems, just simultaneity. Again, when we're talking about panel data structural equations, we have the same problem as before. If we try to estimate it in any way that we would like, it doesn't work. We have inconsistency, and therefore we have to jump into the reduced form way of writing things. How do we get the reduced form? We pre-multiply the whole system times gamma to the -1, and we obtain the reduced form of the system of simultaneous equations. That is the typical way of solving a set of equations. And now what we have is one equation for each of the dependent variables that are possibly endogenous, y, I, t, one for each of them. Which says here that the reduced form also has a structure of error components. That's okay. And then let's look at the properties of the reduced form. The reduced form also has similar properties in the sense that no problem with the alphas, no problem with the lambdas, no problem with the u's, no problem with correlations. So everything is clean. Again, when we are talking about the error components, which are the alphas, lambdas, and u's, no problem. So correlations are 0 and variances are constant. Now let's dive into the actual estimation of the structural equations. The idea is going to be at the beginning always to estimate one equation of a system of equations, and that's by the principle of limited information. And the idea is that we don't want to distribute all the misspecification of the system across the whole system. We just keep the equations one by one. We don't want to disperse the problems of estimating one equation into the whole system. So the idea is we start with just one of the equations. We call it the lowercase g equation, and the lowercase g equation may be the one that is in the position number g, or maybe the first, or whatever. The equations don't have a natural order, so you can think always of estimating the first equation. If you look at a specific notation here, you see that we have a variable which is a dependent variable, is y. Then we try to estimate that y sub g with try to explain it with other variables that are endogenous but are not dependent here, which is capital G, several of them. Then we have parameters for them, gamma, and then we have other explanatory variables that belong into that equation, that is capital X, and then you have coefficients that are related to beta, to the x's that are called betas. Then we have the error. This sometimes is written in a different way. It's written like capital W and then capital thetas, then lowercase thetas. The idea is that capital W means whatever, and whatever includes capital Y and capital X. And then the thetas, say those are the parameters, in this particular case the gammas and the betas. This is the setup here. It is a general setup, and we are talking about one equation that is a linear equation, but it allows for endogeneity in one or several of the explanatory variables. We are not talking about the vector of errors now. We say here that we are often interested in a single equation of the system, and we only consider in this case one equation. Of course, if you want two equations, you first work with one and then work with the other, so there's no problem at all. We are going to use the principle of limited information that prevents the propagation of errors through the system specification. And in this particular case, we are happy and we are lucky because we can estimate by two-stage least squares. That is the estimator of choice. Two-stage least squares is an instrumental variable estimator that uses several instruments. The big problem that we have now here is the identifiability. How do we know that an equation is identified, so that we know what the estimates are, or unidentified or over-identified? Okay, so remember, if it is just identified, you can estimate by instrumental variables, no problem. If it is over-identified, then you can have to estimate using two-stage least squares, no problem. If it's unidentified, it is not estimable, and what you have to do is to specify the equation in order to use, in this case, more instrumental variables. So basically we don't have a big problem here. The problem is not really terrible. This is something that is manageable under a lot of conditions. In general, we would like to have a condition, a range condition, which would be sufficient for identifiability. And that condition is this one that we have here. It's capital K greater or equal to capital K sub G plus capital G sub G minus 1. This is the condition. It seems very convoluted and very strange, but in reality it's very simple, because all it is telling you is that we need more instruments than endogenous variables minus 1. So the idea, you can rephrase it and say we need the same number of instruments or more than the number of endogenous explanatory variables. So in yet another way is, if we have problems with a few variables, with a number of variables because they are endogenous, say we have a problem with 3 endogenous variables, explanatory variables, then we need at least 3 instrumental variables. 4 is better, 5 is also possible, no problem. Okay, so this is the idea. It is a very simple condition when you think about it in the right way. Let's now go to some extra comments. Of course, everything that we have told about is very simply done using stata. There's no problem with stata with that. But let's see how we can make some comments about what we have done. Qualifications. So the endogenous and predetermined variables of an equation act as their own instrument. That's something that we told already. It is very easily implemented. Everything that we have done in stata. And typically, stata helps us correct the problem of identifiability very easily. In this context, it is natural to make yourself the question, that is, what instrumental variables to choose. This question is relatively easy in this context because what we want to do is use the predetermined or exogenous variables that are not present in the equation that we are estimating and in the number that is sufficient for identifiability. Typically, one wants to choose those instrumental variables that are highly correlated with a variable that is problematic, that is endogenous, and the least correlated with the error term. Typically, you choose the instrumental variables that are in the equations of explanatory variables of the endogenous variable that you are going to instrument, and that is the general idea. You have to think of the idea that each endogenous variable is generated in its own equation, and therefore the explanatory variables of that equation are the natural instrumental variables for that endogenous variable that is explanatory in a given equation that you are estimating. The problem also is how many instrumental variables. Well, the idea is not too many, not too few. If they are too few, it is possible to increase the efficiency by increasing the number of instrumental variables. If there are too many, they can reproduce the behavior of the endogenous variable and therefore cause bias in the instrumental variable estimator. So not too many, not too few. That is something that is problematic, but is something that is doable. Some problems with instrumental variables are that they are not unique, and the estimates may vary widely according to the selected instrumental variables, and we don't know exactly if we have the right instrumental variables. Typically, you have some help using the Sargan test, which is appears in some packages but not in Stata directly, but there is a fix for that because you can use a user-defined Sargan test version. Also, the structure of the problem and the common sense will help you decide which variables to use as instrumental variables and which not to use.